Here's a classic question where they're telling us the energy transition that's occurring in a given type of atom and asking you to calculate the wavelength of light emitted. And then from that, they could ask things like, is it in the visible spectrum or infrared or ultraviolet light? What type of radiation is it? Well, here they just want you to calculate the wavelength in nanometers. A couple of things to note. We're talking about the hydrogen atom. There's one proton in the hydrogen atom nucleus, and so the nuclear charge Z is 1. That's important. When we go to use Bohr's equation, the one that relates two energy levels, we'll apply the equation as written like this. Z being the nuclear charge, N being the principal energy level, the final one, and then Z squared over N final, and then minus Z squared over N initial squared. Then, once you get an energy, we're going to use the equation that involves Planck's constant. I like to include number of photons, n times h times speed of light all over wavelength, where n is the number of photons that we're talking about. But if it's just one electron that is making the energy transition, then n would be 1. So if you have one photon making that transition, which will be the case for all of these problems, then we just say, okay, the energy is Planck's constant times the speed of light over wavelength. One other little bit before we start plugging and chugging here. When you solve for the energy, if the energy is negative, it's okay to make it positive when plugging into this equation. So if the energy change is negative, and then we're saying plug it into this next equation, go ahead and make it positive, because it wouldn't make physical sense to get a negative wavelength, at least in our world as we understand it. And admittedly, we don't know what dark matter or dark energy is, so maybe there's something there. But we can't have a negative wavelength. So it's okay to make the energy positive when you go to plug it in. Okay, given that those are our two equations, let's just start working them together. In question A, the transition was from the 5th principal energy level to the 4th principal energy level. So applying Bohr's equation. Go ahead and pull out your calculator and solve for this one. And by the way, your red numbers may be different from mine, but if you had the 5th to the 4th principal energy level, then you'd be along these same lines. Note that when I crunch this, I'm getting a negative number of joules. Go ahead and make that a positive 4.9 times 10 to the negative 20th joules when we go to plug into the next equation. So next equation, positive 4.9 times 10 to the negative 20th equals, since it's one photon, we'll just use Planck's constant, 6.63 times 10 to the negative 34th times the speed of light. We're solving for wavelength here. And when you crunch that, the wavelength works out to be something on the order of 10 to the negative 6th meters. The answer will come out in meters automatically. Now, WebAssign is asking for that answer to be stated in nanometers. Okay, that's easy enough. Nano is 10 to the negative 9th meters. So if we set up a quick conversion factor, 1 nanometer is equivalent to 10 to the negative 9th meters. And so effectively, whatever we do to our number of, if whatever you get in terms of number of meters, multiply it by, or add 9 to the exponent. And in this case, we get 4,060 nanometers. That's our answer to part A. In part B, we're going to do the same thing, just with different numbers. So 4 to 2 in this next one. Pull out that calculator and just start crunching some numbers. And this time it's negative 4.08 times 10 to the negative 19th joules. It's okay to make that number positive. It wouldn't make physical sense otherwise. The exponent, of course, is still a negative 19, but the 4, the number in front, we got rid of. Okay, next equation. Planck's constant times the speed of light. We're solving for wavelength. When you crunch this number, it works out to be 4.875 times 10 to the negative 7th meters. And to convert to nanometers, which is what WebAssign is asking for, 1 nanometer is equivalent to 10 to the negative 9th meters. So that's 487.5 nanometers. Excuse me. That's part B. For C, we're converting, or the transition is from the 4th principal energy level to the 1st. This is an exponent one, sorry. Sorry if that's not clear. And start pulling out that calculator to crunch. It's okay to make this number of joules positive. Keep the same exponent, but make the number itself positive. And then the equation that involves Planck's constant and the speed of light. And in this case, the wavelength works out to be 1.22 times 10 to the negative 7th meters. Quick conversion factor to make it into nanometers as WebAssign requests. And we get 122 nanometers. Once you did it the first time, it goes quickly for parts B and C.